Hey everyone! In the last video, I demoed my project, ClarityScan, which is an app that enables radiologists to enhance their brain MRI scans and also easily identify glioma tumors. If you haven't watched that video, then I'll put the link in the description box below so you can go check that out. But in this video, I wanted to do more of a technical walkthrough about how I structured the project and how I actually implemented the entire pipeline from the data to the model development and also to the application code. So let's get right into it. I've written an article about my findings. I'll put the link to the article in the description box below as well, so you can go take a look at that if you would like to. But we're just going to go through this article together, and I'm going to be sharing some insights on the process of building an end-to-end machine learning project. So to build an end-to-end machine learning project, there are 5 main steps, and I followed these 5 steps to implement this project. The first step is data collection. The next step is model development. The next step is model deployment, then application development, and finally application deployment. And this is the video I was talking about. So in this video, I demoed the application, so definitely go check that out. But just to TLDR, the project is called ClarityScan, and it's an application that enables radiologists to enhance brain MRI scans and identify glioma tumors. And I've got the link here, which I'll also put in the description box below, so you can actually check out the application. Cool. Okay, the first step is data collection. Now, before we can even get to machine learning, we need to take care of the most important stage in the machine learning pipeline, which is the data. Choosing the right data to train or fine-tune your machine learning model can be the difference between machine learning models succeeding and it failing miserably. You know, the common standard of garbage in, garbage out. So here are some considerations for data collection. Training data should be similar to production data. The dataset should be representative of the data that will be fed into the system during production inference. And if this is not the case, you may need to implement strategies like dynamic training to continuously retrain your model. The second thing is to check for class imbalance. If your data is imbalanced, example in this project, which is tumor segmentation, the model will focus most of its efforts on optimizing for the majority class, which is not often the class we care about. And in this case, for ClarityScan, I use the brain tumor segmentation dataset, and we can check out that dataset right here. So this is basically a dataset of brain MRI scans along with the tumor segmentation. So I trained a deep learning model to identify the tumors in these brain MRI scans. Now the scans in this dataset are severely imbalanced because, as you can see, the actual tumor occupies a small portion of the entire scan. So if a model was just trained on this using a naive loss function, then the model would focus a lot more attention on predicting everything else but a tumor. So if you can imagine, if this is the image right here, if the model predicts that everything is not a tumor, then it can actually achieve a pretty high accuracy because this is only a small portion of the image. So you have to formulate your loss function and training objective in such a way that you're actually optimizing for the correct objective. So let's talk a bit more about that. Model development. When developing a model, whether it's a simple tabular data classifier, a deep image segmentation model, or a large language model, there are some important things to keep in mind. And here are some thoughts on developing models. Smaller is better. Low latency is critical for optimizing the end user experience. Aim to minimize the size of the model. Always start with the smallest possible model and then work your way up if required if you need extra performance boosts. Choose the right loss function. This is especially important for datasets with imbalanced classes, and it can really change the trajectory of your model's ability to complete the task at hand. Different loss functions optimize for different goals, and you may have to experiment with many of them before you find the right one. For image segmentation, there are so many loss functions to choose from. cross entropy, focal loss, dice loss, Tversky loss, IOU, and the list goes on. But we need to again ask ourselves, what are we optimizing for? And in this case, since tumors only occupy a small portion of each image and the classes are severely imbalanced, we want the loss function to focus on the minority class. And these are just some of my handwritten notes on trying to evaluate different loss functions and also trying to work out an architecture for the model. But after experimenting with different loss functions, and also I tried combinations of those loss functions, I settled with the dice loss, which naturally optimizes for the predicted image to overlap with the ground truth, and that resolved the class balance issue. But in this case, I didn't have to alter the dataset directly, but in some cases, you can actually alter the dataset directly. This is especially true when you're working with tabular data. So you can use techniques such as oversampling and undersampling to control the class balance. Model deployment. There are several options for deploying models. You can either deploy the model and store the trained model in the application bundle itself, so store it in the website or app bundle. Another option is to build an API or a microservice to serve the request to the model. And the third option is to run all possible predictions and store them in a lookup table. The most common route is to serve a model via an HTTP endpoint. And for deep learning models, you would prefer to use servers that have access to GPUs, so inference can be as quick as it was during training. Now, one of the solutions I found for this is Modal, and Modal is this great cloud provider actually. So it's a serverless platform for basically data and machine learning projects. And what Modal does is it allows you to deploy machine learning model endpoints, and it also gives you really easy access to GPUs, and the SDK is really nice for this. And for anyone who's developing deep learning projects that need that you want to deploy and you want to be able to use GPUs easily, highly recommend using Modal. And you also get $30 free credits per month, so that's also nice to have. So here are some things to keep in mind when deploying ML models. How should you deploy? For small models, serving them in the application bundle should be fine. For example, if you have an object detection model, which can be quantized and served in an app bundle, then you should definitely do that. For models with low cardinality, and cardinality just means the size of the input set. So if I have a model that's just predicting sales revenue for 6 divisions or in an organization, that's really low cardinality because there are only 6 possible inputs for that model. So in cases like that, you can just store all the predictions in a table and you can just pre-compute all those predictions. But for most other cases, you'll have to deploy an API service, which can actually serve requests to the model. Another thing to keep in mind is when you need GPUs for inference. If you're deploying deep learning projects and deep learning models, you can dramatically reduce latency by using GPUs for inference. And again, Modal makes this super easy to do. For ClarityScan, I had 2 models, and you can check out the demo if you would like to see how these models work. But the 2 models are a tumor segmentation model and a denoising model. And so I created 2 HTTP endpoints on Modal to serve each of these models. I have some write-ups on ML model deployment, so go check those out if you're interested. Okay, now into the final stage, application development and deployment. So this is the application, just a preview of the application. So some things to keep in mind when you're thinking about end user experience, and the main thing you want to keep in mind is minimizing latency. So this depends on the specific scenario, of course. In some situations, latency isn't the primary concern, and maybe accuracy is of a higher concern. But generally, you want to reduce the time to answer as much as possible. This could be through minimizing the model size, to utilizing GPUs, and through techniques such as quantization. An example of how I used this technique in my project was for the denoiser model. I was initially using a copy of the segmentation model, and that had around 27 million parameters. And I realized that denoising wouldn't require as in-depth features and as much compute as a segmentation model. So in light of that, I scaled down the denoising model to around 500,000 parameters, and the model actually didn't suffer any performance losses. You should always try to use the smallest model possible, and then scale up from there if required. For the application development, I use Next.js and Tailwind CSS. That's my go-to stack for developing websites. And to deploy, I initially was going to use Vercel because it integrates really nicely with Next.js, but Vercel throttles API requests to 5 seconds per request. And with these models, inference time can take up to 30 seconds to 1 minute, so that didn't work out. Instead, I opted for AWS. I containerized the website application and deployed it to a cluster, put a load balancer on top of that, and that's how we got the application right here. And you can see that URL is using a elastic load balancer. Okay, that's basically the technical walkthrough of the project, of the entire project. Here are some potential areas of improvement for the project. The first thing would be to increase the model scope. And currently the model is able to identify glioma brain tumors. So it's a very specific type of brain tumor. Now, it might be able to generalize to other types of tumors based on the features it has learned. I haven't tested that, but I think it would be nice to expand the model's capabilities to other illnesses, such as AVMs, which are arteriovenous malformations. This could include adding more data, training on more data, or even developing separate models for some of these different illnesses. The second thing would be to accommodate more file formats. Currently, ClarityScan can handle common file formats, including TIFF, JPEG, and PNG. However, MRI scans can be stored in other formats as well, including NII or DICOM. So I think adding support for these formats would be a reasonable next step. Building this project has been an insightful journey for me, and I tend to find that as I develop more and more projects, the scope of the projects increase and also the outputs from the projects increase. So here are some of the resources I created while developing this project. I wrote a bunch of articles which relate to this project. I wrote a guide to image segmentation, which you can go check out here. I wrote a guide to multimodal models, so integrating the data from multiple modalities into a single model. And I also did a write-up on the how I built this project, which is this article which I'm going through right now. And I also did a PDF report on brain tumor analysis, so that's a LinkedIn post which I did. Just a quick carousel on a couple of quick facts on brain tumors and MRI scans. And of course, I created a video on the project demo where I demo the project and the technical walkthrough, which is the video I'm recording right now. And that brings us to the end of this technical walkthrough. I hope you enjoyed learning a bit more about the project, and maybe this has inspired you to go and create your own end-to-end machine learning or deep learning project. And if you have any questions on the architecture for building these projects, some tips and tricks, I would be happy to let you know and help you out. Just leave a question in the comment section below. I would love to hear from you there. All the links will be in the description box below for the application, for the project demo, and all the write-ups which I did for this project. If you like this video, go ahead and smash that like button and make sure you subscribe so that you don't miss out any of my future videos and project demos. With that, I will end the video here and I will see you in the next one. Peace.